We are moving into the section now of Euclidean Geometry, but what is very important, grade 12s, is that you remember that everything you learned in grade 11 is also going to be tested at grade 12 level. And so before we try to build on that, let's just make sure we have a solid foundation and that we know all of the theorems that we should know by now. Okay, so most of our grade 11 geometry is centered around circle geometry, and so that's what we're going to focus on. But the things like parallel lines and angles opposite equal sides, all those kinds of things are still true, and so you need to remember them too. All right, and the best way to do that is to practice, practice, practice. Okay, let's quickly recap. So the first theorem we learned is that if we are given a line, or the first theorem we learned in grade 11, if we are given a line from the center to a chord and it specifically bisects that chord, in other words, this B here is the middle of AC, these two segments are equal, then what we can say without a doubt is that angle B1 and angle B2 for that matter are equal to 90 degrees. So because of that theorem, that is a 90-degree angle, and then the reason there, line from center to midpoint of chord. Now remember, the opposite or the converse is also true. So if you are given 90 degrees, you can deduce then that AB is equal to BC, and then it is the converse of the line from the center to the midpoint of a chord. Okay, this one is great. Second one here, angle at the center is equal to 2 times the angle at the circumference. So if we look at this drawing here, we've got angle C, which is at the circumference, and it is equal to x. And so then this angle O1 here is equal to double the size of that angle. So there we can say angle O1 is equal to 2x, and the reason, angle at center equals 2 times angle at circumference. The next one I find gets skipped over very often. And so what I've started encouraging my students to do is whenever the question specifies that they have a diameter, I tell them to highlight it. Because you don't want to miss the fact that the angle opposite that diameter is always a right angle. Okay, so in this instance, we can say here angle C is equal to 90 degrees, and the reason there is angle in a semicircle. Okay, and that's just a derivation of this second reason that we looked at here. The angle at the center on a straight line is 180 degrees. And so then the angle on the circumference, subtended by the same chord, is going to be half of that, and so it's going to be 90 degrees. Okay, so don't miss out on these sneaky little 90-degree angles that are hiding all over your geometry questions. Okay, then we learned a whole load about tangents. So if we have a look at this, tangent is perpendicular to the radius, very similar to the midpoint one, except now it's a tangent. So at that point, we can once again say, well, angle B1 and angle B2 are 90-degree angles. Why? Because a tangent is perpendicular to the radius. Okay. Then the tan chord theorem. I always think this one is nice to spot. So there's an angle formed between the tangent, okay, which is this line here, and a chord in a circle. So a chord is just a line segment that goes from circumference to circumference. And that one, if you then follow up, so I like to check, okay, where does this chord start and end? Okay, it starts at B and it ends at D. If you follow up from B and you follow up from D, that angle is equal to that 55-degree angle there. Okay, so that's the tan chord theorem at work. So angle E is equal to angle B3, which we are told here is 55 degrees, and the reason, tan chord theorem. Okay, please, you're going to lose so many marks if you don't remember to say statement and reason. I'm just not rewriting them because they are already written there. Okay, and then tangents from a common point. So if you look at that one, you'll see these tangents both originate here from point C, and then this one flows to A, and this one flows to B. Okay, tangents from a common point are equal in length. So what that means is that AC is equal to BC, okay, and that's because of tans from a common point. then because they are equal, we can deduce something about those angles. Okay, so what do we know? Angles opposite equal sides are equal. So because B2 is equal to 70, A2 then is also equal to 70. So A2 is equal to B2 is equal to 70 degrees, and that is angles opposite equal sides. Okay, so that's a little rule we learned already in grade 8, but it's relevant because tangents from a common point are equal in length. And then we encountered this thing called a cyclic quad, basically a four-sided shape where all of the points are on the circumference of a circle. So hence the cyclic for circle, and then quad, four-sided shape. Okay, the opposite angles of a cyclic quad, they add up to 180 degrees, or they are supplementary. So we can say here angle B plus angle D is equal to 180 degrees, opposite angles of a cyclic quad. And so that means angle B there has to be equal to 94 degrees. Okay, because 94 plus 86 will give me a total there of 180. The exterior angle of a cyclic quad, so we've got our quad here, and then the angle needs to be formed by two sides, okay, an extension of the one side and then against or adjacent to one of the other sides. That's an exterior angle, and the exterior angle is equal to the interior opposite angle. So in this case, we can say here that angle A is equal to 100 degrees, okay, exterior angle of a cyclic quad. What I've noticed is that students sometimes forget this, and then they'll first work out angles on a straight line, and then they'll say, opposite angles are supplementary, and so they go the long way around, but eventually they do get the right answer, so that's okay. But it's helpful to save you some time if you can remember the exterior angle of a cyclic quad is equal to the interior opposite angle. And then finally, angles in the same segment. If you find a little shape here that looks like a bow tie or a butterfly, okay, all the points need to be on the circumference. Be careful. If one of them is at the center, then it's one of those earlier theorems, okay? But if they all fall on the circumference, like a true cyclic quad, you kind of have to picture this being closed off to make the four-sided shape there. Okay, but then angles in the same segment are equal. So angle D over there is equal to angle C. So angle D equals angle C is equal to X because those angles are in the same segment. Okay, they are subtended by the same sector here of the circle. Let's test our knowledge here with a combined example. So a circle with center O is given below. TS is a tangent to the circle at T. BC is equal to CT. Okay, that's not on the sketch, so let's put that in. That and that, those are equal. Determine with reasons the size of CAT. So CAT, this angle over here. Okay, what I like to do is I like to take that angle and then follow the sides that form it. Okay, that just helps me to see. Those both begin here on the circumference. So that's a chord. And here's a tangent. So I can definitely use tan chord theorem there for number 1. And we can say angle CAT is equal to 35 degrees. And that's because of the tan chord theorem. All right, and then it is very helpful to then just write those in because you may need to refer to that at a later stage. Okay, next up we want angle BAC. So BAC, we need this one here. Now my gut instinct is to say, well, that's an angle on the circumference or at the circumference. There's an angle at the center. Could I possibly link those? But I don't have any information here, so I can't do that. But what I have got is equal chords here. And so there's a variation of angles in the same segment. I hope you remember it from last year. And that actually says that angles at the circumference subtended by equal chords are equal. So if we follow this chord here, you'll see it makes angle A or A1. And if we follow this chord here, you'll see it makes angle A2. 2. And so those two are actually equal because of that version of angles in the same segment. So we can say angle BAC is equal to 35 degrees. And then the reason there, equal angles subtend equal chords. Okay, not a very common theorem, or at least version of the theorem to find, but it can happen. Okay, and then they want angle BOC, which is now the angle at the center. So now, that thing that I was hoping to use earlier, I can actually use it now. The angle at the center is equal to 2 times the angle at the circumference. So angle BOC is the angle at the center, so it's equal to 2 times 35. Okay, angle at center equals 2 times angle on circumference. Okay, and so 2 times 35 is 70 degrees there. All right, now angle OCB. OCB. There we've got something. If we have a look carefully, we also have, we don't have a diameter. Earlier I said to you it's always helpful to highlight diameters. Another thing that's helpful to highlight, if you are given a circle and they specify the center, is highlight the radii, because every line that goes from the center to the circumference is going to be equal in length. And so simply by highlighting those two, I have just made myself realize, oh, this is an isosceles triangle. These two here are equal, and I know then the two angles opposite that, those are also going to be equal. So then what I'm going to do is I'm going to say, well, let's call these x, just so it helps me to work it out. And I know the sum of the angles in a triangle should be 180. Okay, so let's set this up. So I think the first thing we can say is we can say OB is equal to OC, and that's because they are radii. And then we can say, well, therefore, angle B equals angle C. Angles opposite equal sides or equal radii. That's up to you. Okay, and now we can say 70 plus 2x, those two things I've given there, that adds up to 180. That's the interior angles of a triangle. And now we can just work that out. Take the 70 across. 2x equals 110. So x is equal to 55 degrees. Now what might be helpful, because we never know who's marking our test here, but what we could do at the start of this is actually to say there, let angle OCB, the one we're working with, equal x, just so that our marker knows that at this point here, when we have an answer for x, we have actually answered the question. Okay, so that's 55 degrees, and that's 55 degrees, because they're going to be equal. And then we've got one last one to figure out, angle CBA. So CBA, that's the whole big one there. Now we need to give this some thought. Okay, so what I would like to do there is possibly say, can I figure out, are these two line segments equal in length for any reason? But I can't see that. But something that I haven't used yet, and that's always where I try to work towards, is I have a look, how many points do I have on the circumference? So I've got C, B, A, and T. So I've got a cyclic quad. Even if the question doesn't specify it, but all of these points are on the circumference, then I've got a cyclic quad. And what do I know about cyclic quads? I know that the opposite angles are supplementary. They add up to 180 degrees. Okay, so now what I can say here for question 5 is that angle CBA, that whole big thing, plus angle T2 is equal to 180 degrees. And the reason there, opposite angles of a cyclic quad. Okay, and so now something plus 100 degrees equals 180. So CBA plus 100 equals 180. And so that means angle CBA is equal to 80 degrees. there we have it. So this was a real crash course in all of your grade 11 theorems, but I hope that as you work with them, they come back to you. And never underestimate the power of working through many past papers, because eventually you start to get the hang of things and you start to realize, I can look for radii, or if I'm dealing with a circle, I can look for cyclic quads, and that really helps to guide you along your solving.